Dive into this outline. Today we're going to be covering the ultimate material detective, identifying and measuring phases, decoding the microstructure, industrial quality control, and finally, why this is an indispensable analytical tool.
All right, let's kick things off with Section 1, the ultimate material detective.
If modern material science had a superhero, well, the XRD machine would absolutely be it. It literally forces a substance to spill its most closely guarded structural secrets. Think of this whole setup like a giant blueprint. The automated XRD machine sits right at the center of this massive hub, and every single arrow pointing outward is a totally distinct, incredibly important application powered by this one core technology. We're talking everything from industrial quality control at the top, sweeping right around through semiconductor analysis, microdiffraction, thin films, microstructure, non-ambient studies, and all the way back around to phase identification. It is the beating heart of material characterization across, honestly, just a massive range of scientific and industrial domains.
Now, the absolute most fundamental job of the XRD machine is phase identification. You can think of this as the ultimate fingerprint scanner for materials. It's a qualitative analysis, and it answers the most basic question: what exactly is this stuff? By using X-ray powder diffraction, or XRPD, the machine basically blasts the sample with X-rays and then reads the unique diffraction patterns that bounce back. And because every single crystalline phase has its own completely unique structural fingerprint, the XRD can positively identify exactly what phases are hiding in pure substances or really complex mixtures.
Moving right along to Section 2, identifying and measuring phases.
So knowing what a material is made of is huge, right? But it's really only half the battle. Once we've identified the phases, we need to measure them to figure out exactly how much of each ingredient is actually in the mix. It's super important to understand the difference between these two core functions. On one hand, you've got phase identification. That's qualitative. It's just telling you, hey, you've got phase A, phase B, and phase C in here. But on the other hand, we have quantitative phase analysis. This is the next logical step. It actually determines the relative amounts of those different crystalline phases inside a multiphase material. So we're shifting the focus from what is there to how much is there.
And this brilliantly illustrates that shift. Instead of just handing you a basic grocery list of ingredients, quantitative phase analysis breaks a multiphase material down into exact, bite-sized percentages. Like phase A makes up exactly 60% of the material, phase B is 25%, and phase C is 15%. I mean, if you're manufacturing a life-saving pharmaceutical drug or formulating a highly specific steel alloy, getting those exact ratios perfectly right is literally the difference between a product that works flawlessly and one that fails catastrophically.
But wait, what happens when things get a little chaotic? Because materials in the real world aren't just chilling in a perfect climate-controlled lab, they are exposed to some pretty extreme environments out there, and that is exactly where non-ambient studies come in. See, XRD doesn't just stare at static materials sitting at room temperature. It can actively watch how those crystalline phases transform when we crank up the intensity. We can investigate what happens when we drastically raise or lower the temperature, mess with the humidity, or apply immense pressure using a high-pressure cell. We can literally sit there and watch structural phase transformations happen in real time under stress, which is just mind-blowing.
Let's jump right into Section 3, decoding the microstructure. Okay, I want you to zoom in with me. We're going way past the visible phases and deep into the actual atomic structure of polycrystalline materials. When we're talking about microstructural analysis, we're really evaluating three very specific structural parameters. First up is crystallite size, so basically the diameter of the individual crystals that make up the material. Second is crystal orientation, which is also known as texture. Like, are all these crystals lined up neatly in a specific direction, or is it just total randomness? And third, and this is arguably the most crucial for structural integrity, is residual stress and lattice strain. Are those atomic lattices being stretched out or squished together? Decoding these three specific parameters is exactly how we understand the deepest physical properties of a material. Things like its overall strength, durability, and flexibility.
Sometimes, though, we don't really care about the whole material. Sometimes a tiny microscopic flaw is all it takes to ruin the whole shebang, and that's where microdiffraction really shines. By using a highly focused X-ray beam, scientists can actually perform structural analysis on incredibly small or localized regions in polycrystalline materials. It's kind of like taking a sniper rifle approach to X-ray diffraction. It lets us pinpoint and analyze one tiny specific anomaly or localized stress point on a single component without getting distracted by the rest of the material. And the crazy thing is, this technology scales up to meet the demands of the most advanced industries on the planet.
Take high-resolution XR-XD or HR-XRD, for example. This is absolutely critical for the modern tech world. It analyzes single crystals, semiconductor wafers, and epitaxial layers, hunting for microscopic lattice mismatches or strain. Honestly, this is the exact tech that allows us to manufacture the flawless microchips inside the computers and phones we use every single day. Then you've got Grazing Incidence XRD. By grazing the sample with really low-angle X-rays, it analyzes the crystal structure, the phase composition, and the exact thickness of ultra-thin films and specialized coatings.
All right, let's zoom back out to the macro world with Section 4, Industrial Quality Control.
So, you might be wondering, why does all this microscopic analysis actually matter to us on a daily basis? Well, it matters because massive global industries completely rely on automated XRD as their frontline defense. In mining and cement, XRD gives them rapid material identification, which directly translates to highly efficient production lines. Over in metallurgy and pharmaceuticals, they use it for really rigorous process control to make sure every single batch is perfectly identical, which keeps solutions cost-effective. And for construction materials, it provides the ultimate quality assurance. By catching tiny microstructural flaws before the concrete or steel ever leaves the factory floor, XRD is basically ensuring that the bridges we drive across and the buildings we live in are actually safe and reliable.
Which brings us to our final stop, Section 5, an indispensable analytical tool.
So the crucial point I want you to take away from this is that XRD isn't just some niche, specialized piece of lab equipment. It is an absolutely indispensable technique that forms the very backbone of modern material characterization. Whether you're working in fundamental research, developing new products, or running heavy industrial applications, XRD is essential for figuring out four core things: crystal structure, phase composition, microstructure, and ultimately, material quality. It is quite literally the bridge between the invisible atomic world and the tangible products that we all rely on every single day.
And that leaves us with a pretty fascinating thought to chew on. We've just seen how this amazing technology peers into the very fabric of everything, from the microchips in our phones to the cement out on the sidewalk. But science never stops pushing the boundaries. If X-rays can reveal the invisible flaws in our building materials and guarantee the exact molecular makeup of our life-saving medicines right now, what other hidden, totally revolutionary structures are just waiting out there to be decoded tomorrow? Keep looking closer, everyone. Thanks so much for joining me on this explainer, and I'll catch you next time.